Okay, now I'm going to copy out of VMware just in case if I nuked my hard disk, it would be safe. I just overwrote my previous save point. Dog wants on the bed. Okay, so here is the mission. Oh, you know what? Maybe there aren't any. No. Okay. So the mission is we want to eliminate these. Okay, so they're not C0. I bet that. I wonder if that's it. Okay, so if they're not equal, okay, so this is if it's C0. Otherwise, B1 Rex or not. That's what it is it not? What the fuck? 8B 89. 8B 89. 89 8B 89. If we got a bunch of woos. Why are they not printing? And why are we not? It's an else woo, not a, yeah, it's an else woo. Why are they not printing? What? Oh, it's the later crash. It's a, okay. That's it. Okay. There are none of them. Let's see if okay. there's two of them in a row. Look at that. What the fuck? They are identical. 8B and 8B. So it's two separate instructions. Okay, pass trace. Redundant. So we nuked one of them, but that left a second one. Oh, that's fucked. We're not going to do a stack of them. Okay. This is not... We're not getting the ones we should be getting. Something's very, very wrong. I and J. Something's very wrong. If B48. You know, that doesn't work. Okay. What if that is broken? That would be fucked up. If that is broken, you idiot. No, wait a minute. B2 is not set. No, B2 is right there. If I1 not equal to 1, break. That's if you have a difference. Else if modder. So let's do a progress, a print of progress. Let's look for, okay. You know what? I think the rex, the third bit in the rex has to be compared. Otherwise it'll be broken. No, no, never mind. Okay. So let's do else. We don't need 𝗖𝗢𝗥𝗥𝗨𝗣𝗧𝗘𝗗. Look at that. That is supposed to be redundant. Oh, the C and the 9. Okay. Zero is bit 4 is 0. No. Bit 4 is the other one. Oh, these are 8B, 8B. These are equal, but rex is different. Equal, but rex is different. Okay. So they're equal. B2 modder, B3 B2 modder, it was 4C and 4.9. It was 4C and 4.9. B1 modder. Okay. Is that the only one? Should I double check everything? That's crazy. Okay. Not redundant. Okay. Redundant. There we got some. 440. Okay, we're making progress. Let's only print not redundant. Okay. Oh, we had an example that I could not fix. Okay. There's a 70 RSIRD. I'm not very optimistic. What about other size other than 48? I think we were, oh, what about, yeah, other than 48? What about a mixture of 48 and another one? No, let's see. So what on earth? Okay, I have to go back to the website. And go to, I'm gonna look, I overwrote my file, but what is this? Okay, so if last count equals I minus 3, 8b, R1, R2, J. If the Rex is equal, that's good enough. Okay. I only accept Rex equal to 48. So what about if it's a short instruction? Oh, okay. This gets a little bit dangerous. If the Rexes are equal in the instruction. Okay. Okay, enough of this shit. Get rid of this. Okay, so if the Rexes are equal, what do you say? This is awful, but let's see what it gets us. This is a terrible idea. It'll probably work, but it's a bad idea. I just want to see if it gets our number to the right value. $440, no. Doesn't change our number. What about, we have another, we had it working. Did you know that? We had it working. I think that's what the Rex's, comparison of the Rex's. You know, that's not safe. Okay, what if we do? Oh. let's do this. If hold on a second. They are equal, you do this. Else, if they are not equal, if not I, else. Okay, so we're going to take if not I. We change this to a 1, we get rid of one of these, and we put this in here. If we get a pass, if this. So if that is not that, that is not that. Okay, we get a pass. Okay, so now we're comparing 0, you Control Shift L. Okay, please God, by some miracle. $440, son of a bitch. I hate it when I make it worse and it doesn't get better. Should we do a switch I? I equal 1. Let's see. So we got a pass. Let's put an offset. Has Rex. Has Rex. If you want Rex, B1 has Rex. B1 has Rex, B2 has Rex. If B1 Rex and 40 equals 40. Okay, so now so they both have to have Rex or have to not have Rex. Uh-oh. You know what we do? We, There's some weird shit that happens. If they're not equal, if they are equal, the speed of my compiler is slower, probably. I added junk. Fucking junk. Junk, son of a bitch. Okay. What switch I? No. Okay. J equals 3. 2. Push. They're not equal. Well, $440. shit. Okay. I hate when that happens. So, you know what we're going to do? Okay, we have the drive T mounted. So, let's mount Z probe. It's 10. Okay, now we're gonna copy, let's see. Oh, let's just go there, let's go there. Compiler, backlib. Here it is. Okay. So, T2 MDF reg. T2 MDF reg. Move. Okay. Now, compile. Last count. Last start. I don't think I got it right. Okay. 3A0. Well, that is good news. What's your secret, eh? Okay. So, you know what we do? We, do progress 3. Last progress 3 is progress 3. Okay, we see progress 3 plus plus. Now we go down to here and we say progress 3 minus minus. And we go down to here. If progress 3 not equal last progress 3. Look for progress 3. Unassemble. Unassemble. on in. Okay. It's to unassemble. Yeah. Okay. Trying to see. If. Okay. Okay. What? We got an exact. These are exact 89s. Oh, I know what that is. Okay. Do I know what that is? I don't know if I do know what it is. TempleOS. It's only C zeros. $8B. You got the Rex. Rex has to be identical. The Rex has to be 48. It has to be a 3 byte be, the regs has to be identical in the 3 byte. Last start. What if last start is fucked up? Is that fucked up? Last start. Okay. If progress 3 greater than last progress. Start. What the fuck? What if there are multiple? Son of a bitch. Bunch of redundant. Okay, and 3A0. So 48, it's an equal length. How about, let's, if we don't do it, I know what, let's, no, that's not correct. Okay. Okay, it has a rex. Are they not? Are they completely equal? B. Let's progress 3. If progress 3 greater than last progress. This is a different TempleOS. Let's try that. Let's try that. TempleOS. That stands for lag. Okay. Oh, let's save the L1. How about that? Let's do this. Let's do this. Okay, Control F. TempleOS. TempleOS. Progress 3. Hey, how did that happen? Oh, I got rid of it. Okay. We have serious problems. What the truck? Okay. Okay. We crashed something. set it equal to null. Okay, if not, okay, that's wicked when we're getting some nasty bugs. How about we print it? If. Okay. 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 Dot max. So surely we have to find we're not crazy, right? We're not crazy. Let's see. This has to be true. If no, this has to be true if progress 3, isn't it? I knew that. No, how the fuck did I do that? How come that's... How did we get a progress 3 and not? Are you telling me this, let's see. As Sherlock Holmes says, after you try everything, whatever's left, no matter how improbable, that's it. Hey there. Let's see. I think we can say this. Yeah, okay. It's finally beginning to make some sense. We get a 0 sometimes for that. Let's see. Okay, so this is when we want to this is the problem. What if we do not overwrite it when this happens? Okay. What if we else the increment is wrong. See, I know that. A0. Holy sheep shit. Okay, so we're writing okay, we get rid of this garbage. How about if. Okay. What? We have changed the count. What about the... Let's go ahead and... Is it okay to put this up here. And equals no. Let's see. Well, that was an equal equal? What? I think there it is. Okay, so A0. Okay, so if okay. Okay, combine it. Yeah. Okay. Oh, what if it's the same instruction? Okay, it's a register. Oh. How about, let's save the last end. Why are you being so weird? Let's do this. I think I know what it is. Okay. if you don't know if you fixed it, you did not fix it. What are you doing? Let's go see. So, the pushing the pop. we have to look for move. The push. Okay. Control F, I, C, 0. This puts some, this is for immediate. Pop does that puts some how about we nuke the L1? No. Yeah. No. Yeah, we have to nuke the L1. Let's nuke TempleOS. TempleOS. No. F3. Modder. Correction. /hub. Let's see what I do. Crap. you know what we do? If it's 0, we get a new one. How about that? Let's see. No. Compiler. Let's go ahead and let's Control F to IL1. It was register, wasn't it? That was. What is this? This is. How about, of course, okay. We already tried this. I think we already tried this. A0. We did not try it. Oh, crap. Reboot. Let's see if we can nuke another one farther. Okay. Are you telling me there's a problem with this? There's a problem here. Last end. Okay. So Well, let's... This is ridiculous. How about that? If the count equals 3. Last count. What if it's not the end, but the count? Why did I add a last count? Do you remember? So if, okay, if A0, it's going to be even worse. 440. And it still crashes. Oh, that's... .440 works. 440. Okay. Okay. Oh, and not equal to 3. Let's see. Start. What the fuck was that? 3A0. We did it, but we don't know what we did. We did it, but we don't know what we did. What if we say last end? Is it gonna work? I bet it doesn't work. No, I bet it does work. No, it doesn't work. Are you kidding me? I'm not very confident. I don't know what the fuck's going on. Okay. Let's check this last end. Last end. Where are we going last end? I think we get rid of last end. Count. Last end. Let's see what that does. Let's get rid of it. $500. Shit. Okay. How about, what if we Okay. This is the same one. Same one, different one. Same one, different one. If, oh, what about that? How about that? If. Okay, so J. Let's change J to count. What are you using that crazy? Count. J. Idiot. You idiot. That makes me laugh. Okay, so we do Control F, J, count, rename local variable. Okay. Now, if they are different, then count equals count last. If they are the same, else. they're the same, and we want count equals last start. If count and last start could not last. Or they're equal. Last start equals. What if we let that go? How about we set it equal to 0? If last start. Let's set it equal to 0. This is kind of dangerous. Don't do it. Let's start equal to 0. Last start. Let's reset the last start. Why did you choose it then? Let's see, that's why. What? Oh, I did that. Damn it. Okay. Okay, so what we're doing, okay, no. Okay, so the compiler, if you look up intermediate code, C intermediate code, these are, this is the internal representation of the, when it's compiling, it makes intermediate code, and then it makes the final output code. The intermediate codes have some flags. They have a 64-bit data. This is the line number that the source code line number. What we're looking at right now is the IC body is it compiles each intermediate code into into machine code. IC body has the machine code for the intermediate code, and what we're looking at right now is where did that? That's a base entry, and then there's, oh, there's the base entry. Oh, okay, I screwed up. So it's got the entries are a queue. They're the doubly linked list. It goes in a circle with pointers. Then there's the intermediate code. There's the precedence. This is the count of items in the IC body, and this is the okay. So there are some library routines that operate on there are some sub-intermediate codes. IC move gets used by multiple intermediate codes, and we're working on IC move right now so that it doesn't make a redundant move operation. So what we're doing is we're looking at the IC body with the machine code, and we're analyzing the machine code. It's kind of dangerous to analyze machine code if you don't know where the instructions start and end. And this right here is where the last move started. And so there's a trick. If the last move was in the previous intermediate code, then you have anyway, hold on a second, we're almost done. Okay, should I move it? Yeah, what the heck. So if my hard disk crashes, I won't lose it. So Okay, I haven't uploaded to my site, so my site has the last stable version. Well, anyway. Okay, so here's what we're working on. We're working on we want to check the machine code if it's a redundant instruction. And this crap. Okay. So the format for an instruction, Rex is has been when they made 64-bit long mode, they had to modify the instruction set, and in the original x86, whoops. In the original x86, 40 through 40 up to 4F were set to the increment and decrement instructions. So they used to have single byte. They used to have single byte increment and decrement. So if you wanted decrement RAX, it was a 48. If you wanted decrement R, the ordering is weird, but you say RCX, that's 49. RDX is 4A, and then RBX. Anyway, so what they did is they got rid of these addressing modes. You still have increment and decrement, but you have to do a longer instruction. So increment was 48. So then what they did is the Rex is a prefix that goes on the instruction, and it's a 48 most of the time. What it is the Rex has, okay, so it's 48. The numbers 40 all the way up to 4F are Rex, and they have flags for there are 16 registers in long mode instead of 8, and so the way that you tell if you're using the new registers is there's there's 3 bits in a regular instruction. You have the modder addressing mode is really common, and the modder has 3 registers that correspond to those 3 bits. There's the register across the top, there's a register across the side, and then there's, oh, we're looking at the wrong table. Okay, there's a register across the top, there's the register across the side, and then there's an extended register for sometimes you can use 2 registers in indexed. So for example, so if you want to okay, let's go ahead and ASM. So if you say move EAX, comma, let's look at how we code this. Use let's say 32. Okay, let's look at ECX. Now the order is unassemble here, come 1. So it's 8BC1. 8B is the opcode. In my compiler directory, there's a list of opcodes. Let's go search for 8B. 8B. That is one of the addressing modes of the move. It operates differently in 16, 32, and 64-bit. The CPU has modes. So 8B is that's the R. That's the, I call it the /R RM32 /R RM32. So the /R, the slash instructions are multiplied by 8. That's the way you can look at them. So let's see, we're going by 8 across the top here, are we not? Yes. So the EAX. Okay, so we have EAX and ECX. I think EAX is, I don't know. We'll find out. Oops, shit. Okay, so C1, EAX, ECX. So C1, we can look in this table for C1, and CX is here, and AX is here. So it's it's R32. Now sometimes you can have, now if we have if you have 64-bit, it puts a 48 on the front. Puts a 48 8B, and if you have now we have 3. What? Now we now we have 3 registers, and they call this 1.5 operand. On some machines you can use you can do 4 registers on some machines or whatever, but on x86 there's just 3 registers. There you have register and then the complicated mode, and there's a scale factor. You can go by 2s, by 4s. 8B is the opcode. Then this 4 is going to be an escape. In the table 404, it's going to be an escape. That's going to be, we're looking for the SIB. Okay, 04, here it is. Okay. So it's this footnote. It's AX and it's the footnote. And the footnote table's down here. And that's CXDX 91. 91 is what? Where did 91 go? There's 91. There's 91. Okay, DX times 4, and DX times 4, and CX times and CX. So my intermediate codes are when you compile, unassemble function main. Okay, so you have to allocate registers. The way to understand this is to do pass trace, and this, it goes through passes. It starts with, you call this RISC, reduced instruction set. This is a stack machine. There's an example of a stack machine in my lectures directory. Mini compiler stack machine. So if you say 1 plus 2 times 3 plus 4 times 5. So this is a little 200 line program, and it pushes on the stack, and then it pops 2 and does an operation, pushes on the stack, pops 2, does an operation. It's reverse Polish. So my actual compiler, enter, this is it's already, no, it hasn't decided. Oh, okay, the offset is -8 off RBP is the I variable. It's pushing, okay, it pushes RBP, then it pushes the offset, then it pops 2 and adds them and pushes, then it so let's set that aside. That's the address of I. Then it does another one. It does the same thing again, but this time it dereferences. So on the stack is the address of I, and then at this point is the actual value of I. Now for pointer arithmetic, sometimes you need to, it doesn't know if this is pointer arithmetic, so it's going to multiply by a size of 1. This is kind of a placeholder in case it's pointer arithmetic. Then down here, it's gonna add 1 to the I, pop and add, and then the I plus 1, and the assign operator looks for the address of I. There's 2 things on the stack. These 2 things are on the stack. This pops the 2 and assigns them, and there's no result. So that's how we start. After pass 1, we've identified the classes, the data, the classes correctly. What have we done here? We've looks pretty similar. Oh, we got rid of the add. No, never mind. Looks pretty similar. It's okay. Pass 1 and 2 simplify constants. So if we had let's put a constant here, +2. So at this point we have a 2 and a 1, and then at this point it has made it into a 3. So pass 1 and 2, simplify constants, and figure out the type. It's kind of tricky figuring out the type, because if you now we have a float, and we have to do a conversion. These little flags are conversions. Converts to float, and then it converts back to int. So each intermediate code can have 2 inputs and 1 output. And at the beginning, they're popped off the stack and pushed on the stack. Then it starts using registers. Okay, so that's what this stack is. So they feed off of each other. So after pass 3, the way it allocates registers is it looks at RBP is all the local variables, and it identifies the most common offsets. And the most common offsets, it's not a very, it works, but it's not optimal. It puts the most common offsets into registers. So at this point, it is declared that RSI is going to have the I variable. So everywhere in here, it's now using RSI. Now here's where it starts getting into addressing modes. Okay, so I call this mode is register. These are displacement modes. Actually, I call these displacement modes also because they're zero displacement. Then there's this. Where is it? This mode is oh, there. This is RIP. This is like a global variable in memory at an address. It's RIP displacement 32. In 64-bit mode, it's a relative displacement, so it's a 32-bit number. I put anyway, and then finally, I have a mode for these two register. This is not two register. This is one register. No, wait a minute. What? Okay, displacement. Never mind what I said. This is a 32-bit RIP relative displacement. And this is the scaled mode. So when I make my intermediate codes, I try to make them into x86 instructions as close as possible. So when we get to the bottom, at this point, it has converted them into bigger instructions. Load effective address. This is a way to add a number to another number and get. Normally when you add, okay, there's an add instruction, right? Add 3. Now, how do you suppose you would add? What if you wanted RBX? How would you do that? There's no. Well, the way I'll just tell you, the way you do it is you say LEA. And what that does is it loads effective address. So it treats this as a displacement and an address. So I think we might code it like this. Everybody does it their own way. The syntax. I think this is how I do it. So there's 3 instructions. Okay, so LEA is, when you're doing a compiler, you try to use all the tricks. LEA is okay. We converted to float, so it got really complicated. Let's get rid of that float for now. Okay, so we have, this is my intermediate code, and then this is the final assembly. In the IC body, these are the bytes in the IC body, and there's a limit on it. Each intermediate code can only generate like 60 bytes or something. I don't remember the limit. Anyway, so this coded. We had to preserve RSI. Intel made a standard for how you use registers, but I didn't pay any attention to that. I'm not interested in that. So, for example, they say they use registers to pass arguments. If you you can never avoid saving registers. Either you save them when you call, or you save them when you so I save some registers and I trash other registers. There's a list of the registers that I reg group. So these are the A, B, C, D, and R8. I clobber all the time. They're never saved. Okay, RBP and RSP are saved, and this is a stacked temporary. I'll talk about that. These are local variables. Now it turns out that 12 and 13 are irregular, and so I can't use them for pointers. 12 and 13, if you subtract 8, it's 4 and 5, and in the table 4 and 5 are irregular, so I don't use those for pointers. So as long as you know it's a, so if your local variable is not a pointer, then I can use 4 and 5. See there's a the upper 8 registers behave just like the lower 8, but they have the flag in the rex. In the rex, so you can have so the rex has 40 in these bits, 40, and then it's 41, 2, 3, 4, 5, 6, 7, 8, 9, 10, A, B, C, D, E, F. Anyway, and then these are these tell if it's the upper 8. And then finally there's a size. So 40 is a 32-bit and 48 is a 64-bit. So you'll see 48 a lot. Anyway, so getting back to what we're doing, okay, so what I'm trying to do is eliminate redundant move operations, and anyway, so some of the cases are so if you do move RAX, RBX, so if you just do something like that, or if you do something like if you do something like that, or if you do something like this, or if you do something like okay, so these are some examples. So I'm actually what the oh. So most of my operations I do on the intermediate codes, not the machine code. However, I'm doing these operations on the machine code, and it's pretty nasty. This is something I haven't dealt with yet. I don't really use the 32-bit. Okay, so these don't have the 48. These don't have the 48 recs, and they're only 2 bytes long. So what I started doing was if it has a rex or has not a rex, so when you're trying to eliminate a redundant one, you want them either both to have rex or both not have rex. But the problem is these instructions actually clear out the upper 64, the upper 32 of the 64. Watch this. So this is a problem. I don't know what I'm going to do. I don't know what I'm going to do. So if I move RAX, okay, so if we I have the best assembler compiler on the planet. So it moved RAX to RBX. Then it moved RBX to RAX. Now this should be alarming. Anytime you do a 32-bit instruction, it clears the upper 64 of, or the upper 32 of the 60. So it cleared out the upper BX. So it does, if you know, I hope you know. Okay, so the low order gets put in there. So so if we call this a redundant one, I'm only making redundant the second instruction. So this is redundant. Now what's going to happen? Now it's different. So it's kind of dangerous calling this redundant. However, I know for a fact that any time I move a value into a register, I have extended it to 64 bits. So, well, anyway, so if this goes into a register, it's going to be 64 bits. So this is now some of the pitfalls you have to be careful of. One of the things I just did, if you don't know where an instruction starts, it's really you can't really do anything. You have to know where the instruction starts. And one of the things I just did, which made me nervous, so we're trying to check if they're redundant. If it's the stack or the RIP relative means the position of the code is important, and we would not want to do that. So if I said move AX 0x1000, guess what? These instructions are different. Unassemble here. Did you know they're different? What? Oh. Okay, they unassemble to the same value, but the let's go over how this is coded. It's an 8B, which is a move, and then the modder is 1D, and then the displacement, this is the displacement. So the modder is 1D. Okay, so the modder is 1D. We go to, there's a 16-bit table and a 32-bit table. So the modder is 1D. What did they do there? That's weird. Okay, 1D. So 1D is 32-bit displacement and EBX 32-bit displacement. Now this is RIP relative. In 32-bit mode it's absolute. In 64-bit mode it's relative. So now how did we get this crazy number from this offset? Well, the way you do it is RIP relative. So the address of the instruction here plus 0x10. Let's do the second one. So this is the address of the start, but here's a secret. They always go from it's not from the start of the instruction. It's from this point. So it's +2. So it's from the RIP relative is going to be, so let's see what 0x FFEA plus that. Oh, I fucked up. FFEA. Oh. Okay. It's from the after you fetch it. Okay. What you have to imagine is that inside the CPU, it's decoding this instruction with a pointer. And it fetches this and advances the pointer. It fetches this and advances the pointer. It fetches this and advances the pointer. And so at the time it handles the instruction, the pointer is already advanced past here. And so that's how RIP relative work. Where were we? So it's kind of dangerous what I did. So this move, let's look at an example. Let's this is let's see. Let's do something. C directory entry, file find. Okay, if file find, let's see. So it found it. So here's what I wanted to do. Found, comma, DE. Okay, so it found the file. It got a directory entry. Now we're going to unassemble it and study it. So all this stuff at the bottom is the string constants. That's all the ASCII stuff. It allocates it at the bottom. It Okay, so I wanted to demonstrate the move. Shit. Well, anyway, so when it's doing operations, when it's doing an intermediate code, it does a move to shuffle things around. Then it does, this is like an operation, then it does a move to, so normally it moves to the result. So there's there's two arguments and a result on each intermediate code. There's two arguments and a result. So this is the result is here, and there's two. No, there's not two on that one. Most have one argument. This has. Let's use our head. Which one of these has two? There's load effective address. Okay, load effective address has, oh, there's a displacement as well. There's a displacement, there's argument 1, and then there's argument, then there's the result on the stack. Okay, how about this? So I equals j plus 3. So it's using the displacement again. Let's comma k. This won't use the LEA. I did use the LEA. Oh! Okay. It's using LEA with okay. Well, anyway, they can have two. What's one that has two? How about multiply? No, let's see. Let's do that. Multiply. Okay. So the multiply, R10 is the result, and the two arguments are register RDI and register RSI, and these two numbers tell that it's a 64-bit value. The reason there's two is because there's pass by value and pass by reference, and if I say, let's say these are okay, plus equals. So if I say I plus equals j times k, and they're all U8s, so this gets ugly. So add equal. Now in this case, the add equal is expecting it's expecting the value on the stack, and it's expecting the address of the variable. This is the address of I, and then this is j times k. And when you execute add equal, so there's a the address is actually 64-bit. The address is 64-bit, but the it's a pass by value, and so the multiply is a U8. The add equal, it's a 64-bit address, but the value is a U8. And what I call that is, you'll see that all over the place. So I have this, any of these can be, well, no, that's not true. This is only on assignments is this used. I am pretty sure. I could be wrong. Only on assignments is this used. And you'll notice there's a pointed to type pointed to. Okay, so these types are, the types are a combination of a size up to 64-bit. That's in the low 15, and then in the upper oh, it's a low 64. Okay. There's then it you or one of these addressing modes. So basically, it's putting this number in the low part, and then the high part is the addressing mode. So it's just kind of so then when I do comparisons, I can compare a mode and a size, and when I pass them around, the types are you'll see the types have both the mode and the size, the intermediate mode and the size. So what are we doing? We are, so it's doing a, so this is dangerous. I'm Okay, I'm trying to detect duplicate move operations. And oh well, anyway. Okay, so so the crazy thing, I used to be doing it with a much simpler approach, and it worked better. So I have to find out why. Okay, so I'm going to mount the Z drive. This has my CD-ROM of, this is a backup of earlier today. So I go CD C:\compiler directory. So this crazy thing worked better. So, to make a long story short, I added a lot of lines of code and I made it worse. Oops, that's not where it was. Here's where it was. Okay. Why is it indented? That's weird. Okay, so... Oh, that's why. So if I add this, it's going to reduce the size by about 100 or something. Okay. It appears to be safe. Oh. Okay. Now watch when I compile. 3A0. So it reduced it. It eliminated a lot of so this is crazy. What it's doing basically the same thing. It's comparing the new instruction to the old instruction. This is the start of the old instruction. It's checking the size. This is the one. This is the L means it lags. It lags 1. This is an intermediate code that's lagging 1, and actually it might not lag. It could be in the same intermediate code structure. So it's looking for a So that's pretty crazy. It's checking if it's in. Oh, okay. It has to be at the end of. Okay, this count has the total bytes at the current time, and this last instruction would have finalized it. This is sort of finalized. Actually, it's not finalized, but anyway, so this is checking if we mark the start of the last move instruction. This is the start of the last move, and if it's 3 bytes less than the total, that means anyway, that means it's a 3 byte. We're checking if it's an 8B, and where do we check the we don't check the rex. Oh, I made a poor choice of variable. It's not count. It's that's rex. Oh, okay. Here's where it checks the rex. The rex is it's using negative numbers, so that's so it checks the rex. It checks for R1, R2. So it's surprising that my fancy code can't handle this simple case. It's just an exact. So in other words, it's going to code its register mode. Does modder R1, R2. So the way this old check worked is it bailed out before coding the new instruction. It compared to what the new instruction was going to be with the R1 and R2. Here's where it's coding the R1 and R2 into it's got the rex, and then it codes the instruction. The way the new version works is when we're all done, we check if it's identical, and if it's identical, we move the clock backward. We move the count back to where we started. What if I put the last start? Okay, so why the fuck are we having such a problem? Okay, so this should, maybe I did some, I don't know, I'm just guessing. What if we say last start equals, this is, I'm just guessing. So what if we got some values? Last start is, I'm just giving it a little, let's just see what it is. No, it didn't make a difference. You see, now we're back up to 440 instead of 3A. So we're missing out on, how hard can it be? We just need to print the values. It was the it seemed to help when I kept the this TempleOS if I do this, I can make it work. So let's see if this works. Yeah, okay. So here's the problem. Well, how hard can that be? So I kind of cheat. Well, the last instruction gets updated, so it must be in a previous so the last instruction hey, what if it returns 0 last start greater than or equal to 0? What if it's the last start? Hey, that's not correct. No, that's okay. Last start greater than or equal to 0. What if we set it equal to 0? What if we set this equal to 0? What do 3A? Okay. So it starts let's make it if it's greater than or equal to 0, that's gonna I think we should leave it as a negative. It didn't do anything. It's kind of okay, I'm breathing a sigh of relief. I'm doing really dramatic things. Okay. So let's look for last. I want to check if we compare to 0 or negative. I don't think we do 0. Let's do Okay, so this, in fact, let's see, greater than start. That's start. Okay. Okay. Let's start greater than. What? That's always going to be a. Are you kidding? Wait. Are you kidding me? No, not kidding me. Are you serious? What the fuck? It's not doing it. Holy shit. Let's see. Wait a minute. It shouldn't change if I. Well, I just changed it. What this should be is temp. Okay, never mind. We have to put that back. That was dumb. Okay, so we have to put that back. Okay, so what about maybe the -1? Is that ever going to be a -1? No, it should never be a -1. Should never be a -1. Wait a minute, why are you doing that? Oh, okay. I think we deal with this. Wait a minute. What's this going to do? I don't think it's going to do anything. That's my crash. Okay. Not count. Okay, so it could be another let's find let's do two of them for the time being. Hey, what the we're on the wrong drive. Okay. That would be catastrophic. Okay. So last two. Okay. The more flexible used there. Let's say last two. Last. Well, what? Oh, it's on the okay. Okay, 3A. Hey, do you think we finally got to the bottom of it after all these years? I finally think we got to the bottom of it. I'm so confident. I'm going to delete this. Control F. Flag one. Not. Uh-oh. Oh shit. Did I modify the other drive? Okay. I thought it worked. I was excited. Crap. We almost got it figured out. We're so close. Okay. So if so if the current one has bytes, so if the current one has bytes, how do we deal with that? Let's start. I think we want last start updated. No. Let's see. Last start equals 0. What if we don't do that? If it equals if this is almost the same thing. Let's see. Crash. Okay. We're so close. We are so close. So if temp I count, temp I count. If not, always 0. So if count we do not have any. Feel like making back up. I don't know why. I just like to. So this shirt comes from my parents. They get them at casinos and stuff. I don't know why they have a UFC. Maybe they had a fight in Vegas. I don't know. instruction timings are it all comes down to cache miss, in my opinion. I don't. In the old days, you could manually time an instruction, figure out how many clock cycles, but you can't do it anymore. Perhaps my compiler could be overhauled if a person knew more about the CPU. I make my assembly code out of my compiler look pretty. I make it look pretty like an old school programmer, but the amazing thing is let me show you. Hold on a second. The CPU converts it to RISC, simple instructions, and then it schedules them, and it has a pipeline. The funny thing is, my compiler starts as RISC, and then it makes them into complicated instructions, complex instructions, and then the CPU breaks it back down into RISC. So as a matter of fact, when I first made my compiler, I didn't have optimizations, and I did it like this, and it really doesn't make much difference when you make more complicated instructions, because the CPU breaks them into RISC all over again. I could be wrong, but I got really excited when I added a new optimization, but then I was disappointed because it didn't do much. And it turns out we can both learn ourselves. We don't want 486. It tries to do multiple instructions at once. Might help if I read this. it breaks them into risk. We could do an experiment to get rid of my optimizing. The only problem is it's mandatory. Okay, so we're real close on. We're real close. Son of a bitch. Let's get this. So let's do last instruction 2. Is this going to fix it? That's what it. Let's just see if this should be equivalent. This should be equivalent to what we have. So count, I see. So if it's the previous instruction and we have some values, let's start. Oh. If count and last start not equal to 0. If this has a count, the last start is not 0. Let's see what that is. Crashes. Okay. It's they're different. And we have bytes. So if the previous move is in the current intermediate code, then the count is from start to there. Else, this means they're different. If we have bytes, and what happened when we did last start? That was not enough. What if we advance last start? I see count minus last start. I see count minus last start. Why? This should be last start. No. Let's see. Yeah, this should... Are you saying this is not enough? Let's see. Doesn't work. Of course that should work. And if we say or, yeah, this will work. Okay. So count. You know what I want to do? Let's count 1 and count 2. Count 1 and count 2. What is this? Hash rate. It should be I. Count 2 hash rates. 2 plus hash rates. Are you serious? I think that's wrong. 1 is the old, 2 is the new. Okay, oh, let's do that. Oh, let's see. No, that's not right. Let's start. It's the count at that point. Why don't we, let's print out a value. Print. Okay, so let's use our head. So this is where we need to print. And let's unassemble an instruction. Let's see. If damn, that's not going to do much good. Start 10. How about if unassemble, just unassemble. Okay, we have to get smart. Gotta get smart. Fucking around forever. Okay, so now we say just debug on. What was all that? Wait a minute. Start 3. Just debug on. It's shorter, but it's not showing up. B0. What the truck? Shorter one's not showing up. Oh, okay. Not that that matters. Why is it not showing up? Fuck. Oh, let's look for sysdebugs. I have multiple sysdebugs. Okay. Okay, now let's... $360. Well, this is not going to work. Why did it not? It worked. Oh. 440. Oh. That's fine. Progress 1. What? there was a crazy thing that happened. Oh, it's not in the compiled code. It's in the live code. Okay. So, we need to print out where it is in the live code. Okay, so we go to that. It's going to crash it. But that's how we learn. Okay, now we do a sleep. Different result than what we normally would. idiot. 𝗖𝗢𝗥𝗨𝗧𝗘𝗗. Last start 03. What about just for caution. Let's go ahead and do the finalize. No. Okay. Finalize. Oh, that's what we can do. Okay. We're gonna do this correctly. If. that? Let's do the C0 on them. Let's do the C0 on them. Some of that. Okay, so this will work. Last start. Okay. So okay, so if let's see if this works. It works. A0. Okay. So now I'm going to compiler. Hey, we did it. Fucking did it. Okay. Control Shift L. count 1 and count 2 are all fucked up. Is that correct? Oh, it's instructions. We're just going to speed this up a bit. Drive C. Lib. Or Less than or equal to 4. So the greater than 4s are the problem. Less than or equal to 4. Let's do 1. Let's see. Shit. Okay, so let's, if it's ahead of time, back when, if ahead of time, CC sick. It is sick. Reboot. Flags. Okay. Lesson 4. Okay. Crap. I hate when that happens. Shit. You're shitting me. Let's see if find EOT works. Oh shit. 4, 5. Oh, what if it's let's see. Okay, let's get this over with. We're real close. Okay, let's get this over with. We're real close. Okay. Let's see if the find FD. This is fucked up. No, it's not fucked up. It's not fucked up. Ooh. Okay. Holy shit. Okay, so it's working. Could we pass a test? Okay, you think we could pass a test suite? Let's see. Let's see how good it is. Lesson 4. Okay, so know. We're gonna only do 64-bit. We can see if we can pass the test suite. We're down to 390. That's good. I guess less than 390 is bug. We were down to 360. It's possible this will be a compiler optimization. Okay, so let's look for 𝗖𝗥𝗥𝗨𝗣𝗧𝗘𝗗. 𝗖𝗥𝗥𝗨𝗣𝗧𝗘𝗗. We gotta trim this down a little bit. Okay, we can live with 40s. No, we can't live with 40s. Let's just do 48. 48. This is going to be very cool. Okay, 𝗖𝗥𝗥𝗨𝗣𝗧𝗥𝗥. Okay. If 𝗖𝗥𝗥𝗨𝗏 and 𝗖𝗥𝗥𝗏. Get rid of one of them. Okay, let's see, we're almost done. We are almost done. Okay, we're at 390. Okay, the question is, what's up with these? Let's unassemble. This is for let's put us asleep. This is milliseconds, microseconds. Okay. Let's let it rip. What the heck? Let's boot them back up. Back up. Drive C. Do you think it magically got fixed? Maybe. We can hope. We got rid of the no, it did not. Which one of these? Okay, let's compile the what if we compile with the D drive and boot it? Okay, so if we compile with the D drive and boot it, it's going to be broken. Okay, it's broken. So if we compile with the D drive, so that means it's the just-in-time code during startup. Or I guess that's not necessarily true. No, it's the just-in-time code during startup. So let's okay. So not if is sysdebug or less than 4. Okay. Otherwise, IL1 count. Cur1, cur2. Last start. Last start. Okay, and busy wait. Busy wait. 3:00. Okay, come on, let's get to the bottom of this. Get this over with. Okay, so hey, what was that last one? We gotta do raw. Okay, let's see. Let's just debug on. Compiler. Gotta do raw. Raw. Let's just divide and conquer a little bit. Let's say B1 or B1 R1 not or not R1. Let's see. So just debug on. That's got RAX. That must be the other one. RAX to RAX. Oh, that was it. RAX to RAX. Ha ha ha. Thank God. Okay. Let's boot the backup. RAX to RAX. Okay. Drive C. Compiler. You idiot. You idiot. Okay. I'm so confident that we are going to. We are going to, let's see. Progress. Progress 0. On. F3. Progress equals. Okay. Can get rid of all this crap. We're gonna get done. Done. On to the next one. Oops. Okay. That. Okay. So if it's a displacement and you go to the same register, it makes a difference. Okay, so if they're equal, 1, water, O3, C0. Otherwise, if they're equal and not C0, else. There's two registers, remember. There's the index registers that are do we want to do that? I guess so. Okay, let's just do it. Do you remember this? This is for, okay, so we're almost done. Okay, hurry. Let's just, let's see. Okay. Count equals 3 and all that shit. Let's just do a big else. Why don't we, let's see. These are used. Else we want to do a break if it's displacement in okay, else hold on a second, okay. Let's do this. Let's just cheat a little bit. Okay, we're looking for an equate here. This is we're not cheating, we're just going faster than. Okay. Done, I'm done, and I'm on to the next one. Okay, so this should work. It works. Unnecessary parentheses. Semicolon and break. Why is God laughing? Shit. God's laughing. Look at that, 360. We made an optimization. At the end of the day, it's better. Okay. I was hoping. Okay, so it's better than it was, not worse. Okay. So what we have to do is the SIB SIB mode. If we could just get rid of that. I think that's what God was laughing about. Could be. Okay, so if they equal each other, or sometimes judgment. SIB. All we have to do is SIB. Then we can get rid of that register 3. say, call it a day. Okay, so supposedly my code is more important in some cases. If B1 equals B2 or SIB or Rex is not equal or oh shit. There's another case. What if they're equal? This is if they're not equal. That's what God was laughing about. I hope. Okay, so you see these two would end up being equal. And if they're equal. Okay. I think we're okay, aren't we? We're okay. We caught it. Wait. These two are equal. We caught it, didn't we? Okay. Hey, we already have the Rex 48. Okay. If not I. So did we, you want to start from 1? Not I is not an issue. Okay. We didn't compare the regs. This could cause a problem. Do we have any warnings? No warnings. I'm worried about the regs. $360. Okay. SIB in case you're, let me explain the SIB. So when you have the 3 register version, you get that by using number 4, number 44, number 84. You get that by using that, and then what happens is you have another byte added to the instruction, and it's this byte, SIB. SIB, I don't know what it stands for. Anyway, so there's 3 registers, and if what we would have to do it perfectly, we're more worried about we want our code to be pretty. It's not worth it. It's a judgment call, and it's not worth it. I would have to check if I'd have to get the next byte, and then it's not worth it. Fuck it. It's never gonna happen. Okay, so what about the Rex? Are we okay? So with number 1, okay, we're using the Rex. The third one we're not looking at, but that's because it's not used. So if the Rex, if they're equal, what if the Rex was not equal, but everything else was equal? We would start with 1. We would get you think we should start with 0? No, let's not. What if it's not 80, 89 or 88B? I think we should nuke it. Let's nuke it. Okay. If they are equal, it's never going to work if it's never going to happen if they're not equal. If they're equal, they're not equal. Okay. So the Rex, what about the Rex? So it's in here. B1. What if the rex does not equal? I think we have to put the rex in here. They are equal. First of all, let's see if this works. Uh-oh. E0. E0. Oh, 3. What were we? 3, 9? I don't remember. Three, 9, that's what it was. What was I saying? We 360. Yeah. Okay. Let's check the rex. How about that? Well, that's what we just did. No, we put a break. What about that the third bit? But the third bit we're not using. If it's C0, the third bit of the rex. Wait a minute, they're equal. What about the third bit of the rex? What about I think we want to say the rexes are not equal. So if it's not that, then number 3, else the x's are not equal, break. Okay, I think we're done. $360. Good. Okay. So, well, now there's what we started way earlier. Control F. Okay. How hard can this be? This is false. Let's look for sysdebug. False. Okay. Should we back up? Let's back up. This can't take that long. Oh, I guess it could. Okay, so let's see. Okay, we're going to back up. Look around a little bit. Okay. And so we went from A0 to 60, so we saved a lot of bytes. Yeah, sorry. Sorry, I don't talk more. Okay, so we started today looking at I equals J equals value, double assignment, and we discovered that I had a bug for or equal and equal and stuff like that. And so when fixing the bug, it introduced redundant code, and I started doing special case checks for redundant code, but then I decided to modify the main move to detect redundant code. So let's see if we can pass a test suite. It's good to okay, I'm going to copy it out of my VMware. I'm not ready to put it on the site yet. Pretty close. We're almost there. So I can sysdebug. Now that I'm warmed up, I should be able to find this really fast. Okay, so what we're talking about is okay, F0C or store it. B, store it. Or store. Okay. Looks good. So that's what we started with. Now we want to find, why don't you use your head and find What is this? How do I make this happen? What's the bug? You know, I could try it and see if it crashes. Oh no, I have to try it. That's the problem. I think it does crash, as a matter of fact. Yeah, okay. Well, now we have to find it. So, what is your malfunction? Why would it crash? Oh, it's... Okay, so... I don't know how to make this happen. I guess this is what should... Oh, this is how you make it happen. But it doesn't always crash. So the way you make it happen is this way. Let's try and isolate why it crashes. Let's see, line 110. Oh. I could swear we looked at this. Hey, you know what? Oh. This is an equal. I think the equals are okay. Could be wrong. If it's an assign, if it's a flat assign, let's see. If. This is the main opcode. Let's see if it works. Code. Opcode is crashes. I was hoping it wouldn't crash, but it did. So Is this with 2 in a row? What? The assign might be the second one. It's an LEA. Let's load absolute, load effective address. Oh, well, we won't check that then. Okay, so well, we might as well limit okay, so some of these are crashing. One. Most of these are probably okay. The question is, where is it crashing? Oh, you know what we can do? Let's go to let's go to the game's Eagle Dive. Now what we do is we turn on sysdebug and turn off sysdebug. Oops, nope, did it wrong. Let's put it at the top. Okay, we're trying to produce the error, and this is not producing the error. So, what can produce the error? What about the compiler? Let's see. If I put sysdebug and then compile the compiler. Okay, so we're going to check if the compiler malfunctions, if it makes bad code. Wait, what are we checking? We're checking if the bug happens. Okay, now we reboot. Yes. So the compiler code, what about the kernel and the compiler? Let's see if the compiler, I compile both kernel and compiler. So, wait, where are we? So, compile. Okay, you know what I'm doing? Okay, now I'm going to go to the make all. And say sysdebug on, sysdebug off. Okay, so I don't want to mess with the kernel. I do want to mess with the compiler. Okay, now we are compiling, and so the compiler broke. That's good. Okay, reboot. So now we want to look. Let's see. to start looking at some of these. 103. Shit. 40, 40, 40. Okay, what if it's the FS? Why would it be the FS? Maybe. How can we deal with that? Let's see. Why would it be the FS? What are we doing? We're making the result equal to the previous one. Let's just try this. Let's go to home. Drive C. Okay, now we want to go to the make. By some miracle, maybe we will find it. Let's see. So the quick way to do this is just AX. AX to SI. There's a double. What's that? Oh no, it's not double. Why did it do that? CDB8C0. CDB8D0. Do we have extra ones? Wait a minute. Okay, let's eliminate what's good. So okay. Let's see. So move C to AX. C8. C8, C8 to D0. This is C8 again. BX. C8 D0 again. Okay. Then BX. Then BX. Okay, got right. D0 to BX, B8, RSI. Well, it's pretty fucked up. Now we got good. The hardest part is reproducing a bug. Okay. Although whatever I was doing earlier today was pretty hard. Okay, so so AX assigned C8 this is by value D0 C8 D0 by value D0 B8 this is by value B8 C0. So the intermediate code's good. It's the code generation. The code generation is what's fucked up. Uh-oh. That might be what we just worked on. Okay, so don't. If these are good, then it's good. And these look good. Those don't look bad. So we want to look at the assign and see what the fuck is its problem. Okay. It's not used to doing that. We want to go, so the assign calls IC assign. IC assign. Okay, what is this? Back C. Okay, so I'm just setting the place. Back C. Okay, it's by value. How hard can this be? Look how simple this is. It's by value. So move argument 2 to argument 1 with the pointed to type. I don't think that's a problem. And if register, oh, look at this. Why are you doing that? What the hell is this? Oh, pointed to type. If register R1, R1, R1. Hey, this is A1 instead of A2. A2 is, let's move A1. What do you say, folks? Let's move A1. But the sizes can be different. A2 and A1 can be different sizes. If A1 is a register, let's stick to A1. I don't think we're gonna. Okay, so let's compile and take note of 360. Oh shit. Reboot. I think what about A++ and B++? Or C? So 2, I think we have to, why don't we always do this? Let's do that. This is a change to the language. Okay, that's good. Okay, yeah, we're gonna always do that. Okay, so now we go down. So the issue was, oh, we didn't test it. Okay. I hope it works, God, please. A. All right, actually, let's. that's the result. BX, RBX down. Well, that's the craziest thing I ever saw. That's the craziest thing. Are you kidding me? Okay, so now let's just debug on. Oh crap. Son of a bitch. Okay, so that was uh-oh, what about the size? I forgot to check the size. I don't know, not that it... Oh no, we increased the size. I think we live with it. Fuck it. Try this debug again. Okay, definitely does not work. What about if it's not by value? It is by value though. What's this MDG mask? Oh, yeah, okay. You know, for speed, I think it would be faster if it does it in parallel. Anyway, we got bigger problems. What about the plus plus and the other ones? End branch, bit ops, Q remove. All these. Okay, so okay, I'm gonna walk to the store. I'm going to the store to get some food.